Hello, in this video we will discuss two particular examples of the Bayesian risk minimization. And to start with, we will take as a starting point the general estimation problem. Remind, the goal of the estimation problem is to design a system that we call the estimator that, given any observation x, produces an output S hat which is in some way similar to the value of some target variable S. Under the Bayesian risk minimization approach, we will assume that we are given a cost function C, which states what is the penalty of using S hat as an estimation of S. Okay? And the estimator is selected in order to minimize the expected value of the cost that we usually call the risk. And, well, analyzing this problem, we have discovered that the general solution to this problem is given by searching for every value of x, the value of S hat minimizing the expected value of the cost given x, which is the conditional risk. So in this video, I will analyze this solution in two particular cases. The first one is the square error. So in this case, we will analyze what happens when the cost is given by the square error, which means the difference, the square difference of between the true value of the target variable and the estimation. In that case, the risk is equal to the expected value of S minus S hat to the square, which is usually called the mean square error, or MSE. Okay. So the estimator will be called S hat sub MSE, and according to the general solution, it will be given by the value minimizing the expected value of S minus S hat to the square given x. Okay. So, well, I will expand the conditional risk, and after that we will minimize it. So the expected value of S minus S hat to the square given x is equal to the expected value of a square given x minus 2 times the expected value of S given x times S hat plus S hat to the square. Okay, we have computed the square of the difference, and I have taken out from the expectation operator all constant terms, and, well, take into account that S hat is actually a random variable, but it is a deterministic function of x. If x is a condition is assumed to be no in the expectation operator, well, S hat is no longer a random variable, and we can just take it out from the expectations. Okay? So note that this expression is a quadratic form in S hat as a function of S hat, which is the variable that we have to minimize. Okay? This is a quadratic form, so we can plot it here. expected value of s minus s hat to the square given x as a function of s hat is a quadratic function. Okay? And well, we have to minimize it. Where is the minimum? Well, the minimum is got simply by computing the derivative with respect to a hat, to s hat, and taking out s hat. So, just by differentiation, we can see easily that Mse is equal to the expected value of s hat s given x. Okay? That is the minimum mean square error estimate is given by the conditional mean. So the value minimizing this function is the conditional mean. Okay? And the minimum value of the square error, expected value of s minus s Mse to the square given x is given by the expected value of s minus the expected value of s given x to the square given x. And this is just the formula for the variance of s given x. So this is the variance of s given x. That is, this value here is the variance of s given x. Okay? So this is, well, the three main equations in this solution. We have got a formula for the risk, for the conditional risk in the case of the square error. We have got the minimum, an expression for the minimum, and we have got an expression for the minimum possible risk. We can also prove an interesting property of the minimum mean square error estimate, which is that well, we can write it as a theorem as MSE is an unbiased estimator. Which means that the bias of the mean square error estimate is equal to 0. Okay? And well, the proof is quite simple. We can see that. To see that, we can compute the conditional bias. The conditional bias is just the expected value of s given x minus the expected value of the estimator s hat given x. Okay? That is the expected value of s given x, and in this case s hat is Sm the minimum mean square error estimate, and well, the estimator is a deterministic function of the observation, so this is just Mse. Okay. But we know that we have seen that the mean square error estimate is exactly this. So the expected value of s given x is also Mse, and therefore the conditional bias is 0. Okay, and the bias according to this, the bias, which is the expected value, the expectation of the conditional bias with respect to S, and the bias is the expectation of S minus S hat, okay, which is the integral of the conditional bias. And the conditional bias is 0, so the integral is 0. And this completes the proof. Okay? So, for no matter what is the distribution relating S and X, the minimum mean square error estimate is always unbiased. Now let's assume that we want to minimize the risk for another cost, which is the absolute deviation. So let's assume that the cost now is given by the absolute difference between S and S hat. In such case, the risk can be called the MAD, or mean absolute deviation, that is the expected value of the absolute difference between S and S hat. So we know that the estimator minimizing the risk is given by the general solution. We will call it SMAD, and will be given by the value minimizing with respect to S hat, the expected value of the absolute difference between S and S hat given X. Okay? So I will expand this expression just to minimize it, the expected value of the absolute difference between S and S hat given X. This is an expectation over capital S, because S hat is a deterministic function of the observation, and the observation is known. So this will be equal to the integral of the absolute difference between S and S hat times the posterior probability density function of S given X differential S. Okay? And this integral should be computed from minus to plus infinity. Well, in order to remove the absolute values, we will decompose this integral into four into halves. The first part will be the integral from minus infinity to S hat, and the second part will be the integral from S hat to infinity. Okay. And know that in the domain of the first integral, S is smaller than S hat, smaller or equal, so the absolute difference between S and S hat will be given by the biggest value minus the smallest, that is S hat minus S. And in the other domain, we will have that the absolute difference is equal to S minus S hat. Okay, so we have now removed the absolute values, and we can now split the integrals in integrals with the first term and the second term. So the first term here will be S hat times the integral of P of S given X, S given X differential S, minus the integral minus infinity to S hat of S times P of S given X, S given X, differential S, plus the integral from minus infinity to plus infinity of S times Ps given X, S given X, differential S, minus S hat, integral from S hat, S hat to infinity of P of S given X, S given X differential S. Okay. So we have four terms here, and now we are ready to compute the derivatives. We want to minimize with respect to S hat, so we will compute the derivative with respect to S hat of the conditional risk with respect to S. Okay, and this will be equal to, well, we have a product here, S hat times the integral, so the derivative will be the integral plus S hat times the derivative of the integral, and this is equal to the, since the S hat is just the upper limit of the integral, the derivative will be just the integrand, so this is equal to P of S given X of S hat given X. So we have this integral solved. Now we have to compute the derivative of this. This is, and by the same reasons, the derivative will be the integral P of S given X, S given X. And now we have to compute the derivative of the next term. And, well, this integral is from S hat, sorry. And here we have to compute the derivative of the integral with respect to S hat, and S hat is in the lower limit, so the derivative will be equal to the integrand with minus sign. So minus S hat P of S given X, S hat given X. Well, and in a similar way, we can compute the integral of the last term, which will be given by minus the integral S hat to infinity of P of S given X, S given X, plus S hat P S given X, S given X, X S hat. Okay, so this is the integral, and we can see here that this term, this term, this term, and this term are all the same with opposite signs, so they cancel each other. So we have only two integrals remaining. So if we compute this derivative over the minimizer, so if we compute S hat over the minimizer, that will be SMAD, okay? That is all this sum computed over SMAD, the result should be 0. Okay, so in the minimum, if we move this to here, for S equal to SMAD, we have that this integral should be equal to this one, the integral from minus infinity to S MAD with the posterior distribution of S given X, differential S, should be equal to the integral from S hat MAD to infinity of the posterior distribution of S given X. Okay. Well, and this means that whatever is the shape of the posterior distribution as a function of S, SMAD will be the point splitting the distribution in two halves with the same integral. The integral of both sides should be 1, so each side should have integral equal to 1/2. Okay, so and this point has a name in statistics for any distribution. Any point splitting the distributions into parts with the same area has a name. It is the median of the distribution. So SMAD is the median of S given X, or the posterior median of S. Okay, and that's the solution. Note that in some cases this median can be not unique. Right? For instance, if we have this distribution and the area here is 1/2, and the distribution takes value around here, well, in this case, any value in this region is a minimizer, so any one of these values could be taken as MAD. Okay, but in general, we will have a unique solution.